Well, I'm going to talk about problem 4 and problem 8, but first I want to just say a little few words about some general ideas, trigonometry ideas that apply to both problem 4 and problem 8. In the first place, it's convenient to build these triangles or think of these triangles, especially with acute triangles, is to think of them in a circle like this where we have the four quadrants. Remember the four quadrants. So all these an acute triangle is going to stay inside the first quadrant. In other words, you can make a triangle like this. It stays it's in this first quadrant. Here's another triangle like this. This would be a bigger triangle where this angle here is pretty small. Now, this angle from here down to here is a bigger angle than that. And then I don't want to get this all cluttered up, so I'll show you this on another page that I made. But the point is you have various triangles. Now, one thing that I should say, here's the radius. The radius here, or the radius of the circle, the radius again, we're always making the radius be the hypotenuse of the triangle. You see, this triangle has got a smaller angle right here, but the hypotenuse goes out like that. Then the hypotenuse of this one is the same because it's the radius of the circle. Now, you can make a lot of triangles in the first quadrant, but I guess I got to show them like this. Yeah, oh, they fit, good. The point is, all of these 8 triangles, I didn't want to make the whole circle for them because, you see, it would take up too much room, but this I could have shown them inside a circle where this is in the first quadrant. All of these triangles are in the first quadrant. But this is like a small one, 5 degrees. This is a little bigger, 10 degrees. This is 20 degrees. This is 30 degrees. And this angle right here, anyway. All of these have the same hypotenuse, as I'm showing in this picture. So I only drew the whole circle around this one, you see, because if I didn't want to, there wasn't enough room to put 8 circles, but 45 degrees, 60 degrees, 70 degrees, 85. 85 is almost 90. You can't really even draw a 90 as a triangle because this line here would become straight up and down, the radius, and it would coincide with the opposite. The same here, you can't really draw 0 degrees because you could maybe try to draw a triangle with 1 degree, but in this corner here. So anyway, let me move on to something else because there's one more idea I want to show you here, which goes something like this. The sine, cosine, do these fit like that? Oh, they do. Oh, that's nice. Now the thing is, let me make a triangle like this. This is supposed to be a 40. Well, no, let's make a 30-degree triangle. A triangle in which this angle right here, this one, is about 30 degrees. Now, the sine of 30 degrees, or the sine of any angle, actually. I should have started in general. Wait, let me back up slightly here. Let's just call this theta. Right, when we don't even know that it's 30, although I am going to use 30, but let's make it a little straighter than that. But point I'm making is the sine of theta any angle, any acute triangle, I could have, this be 45 or 60 or whatever. The opposite side, let me just put OPP for opposite. The opposite divided by the hypotenuse. And the cosine of theta, of the angle, is the adjacent side, the ratio of the length of the adjacent side divided by the length of the hypotenuse. Now I can call this 30 degrees. We happen to know, you can in fact look it up on your calculator to check this. We happen to know that, and I'll fix up this circle a little better. We happen to know that if the length of the radius is 1, the adjacent side is always going to be half that length, or wait a minute, sorry. The opposite side is half as long as the hypotenuse. The adjacent side is something like that. That's always true when you have 30 degrees. I'll put the sine of 30 degrees equals 0.5. You could look it up on a calculator, the cosine of 30 degrees. Now one more thing about that. By 866, it's even a weirder decimal than that. But you know what this really is? It's the square root of 3 over 2. It's the same thing as point. Now, why is it the square root of 3 over 2? Well, because, remember the Pythagorean theorem, a squared plus b squared equals c squared? Let's say we didn't know how long this was. We didn't know it was the square root of 3 over 2, or 0.866. Let's say we just know these two sides. Well, this side, let's say this side was A, and this side was B, and the hypotenuse was C, then A squared plus B squared is going to equal C squared, which means 0.5 squared plus, we don't know this, B squared equals C squared, which is the, actually 1 squared, remember, because the length of this is 1. So now we can use this to find what's the length of this side here. 0.5 squared, oh wait, can you read everything I'm writing? I better move this down so you can read it. Fortunately, you can still read it. I'm getting to the bottom of this page. 0.5 squared is 0.25. I just know that. I won't worry about that. Half of 0.5 plus b squared equals 1. Almost ran out of room. B squared, I'm going to put the 0.25 on that side, is, I should have used fractions with this, sorry. That's 3 over 4. Let me do this again with fractions. Sorry. Wait, let's say this. Let's say this using fractions instead of decimals. Okay, I call this 0.5. Let's call it 1/2. It's the same thing as 0.5. So we have 1/2 squared plus b squared equals 1 squared. 1/2 squared is 1 over 4 plus b squared equals 1. Now I'm going to go up in here so we can still see what's going on. This isn't coming out really dark, is it? It's too bad. Okay, let's move the 1/4 over on that side. B squared equals 3/4. Now we'll take the square root of both sides. The square root of b squared equals the square root of 3/4, which is the same thing as, we got room here? The square root of 3 over the square root of 4, which is the same thing, and by the way, this is b, right? The square root of b squared is b. And this becomes the square root of 3 over... See, I was just deriving, in case you're wondering, why is this side in a 30-degree triangle always equal to 0.866? Well, it's really, this side is the square root of 3/2, which if you do that in your calculator, that's what you get, 0.866. And the opposite side is 1/2. So, I think that'll sum that up.